Sound is a sequence of waves of pressure which propagate through a medium. These mechanical vibrations are created by a source which causes the surrounding medium to vibrate. Most commonly, these mediums are air or water, but can be a variety of other materials. We will explain how the sound of a guitar travels to your ear. First, when someone plucks the string of a guitar, the strings vibrate. The strings in the guitar vibrate in a transverse wave pattern. Let's say the length of the guitar string was 1 meter long. Hence, the wavelength will be 2 meters long. Let's say that we produce the note C. Its frequency is 256 hertz. Because wavelength times frequency equals velocity, the velocity of the spring itself is 512 meters per second. Now let's take a look at the properties of the sound wave. The approximate velocity of sound through air at sea level is about 340.29 meters per second. This speed varies by temperature. The transverse guitar wave wobbles out of the guitar and produces a longitudinal sound wave with equal frequency. Thus, the frequency of the sound wave equals 256 hertz. As you can see, the frequencies and consequently their periods of both the longitudinal sound waves and the transverse guitar string waves are equal. Because we know that frequency times wavelength equals velocity, the wavelength is 1.3 meters. As you can see, their wavelengths, amplitudes, and velocities vary. The speed of the longitudinal sound wave is faster because it is traveling through a less dense and less rigid material, air. We will now move to discuss how the sound travels to your ear. The back and forth vibrations of the surrounding air molecules create a pressure wave outward. These vibrating air molecules do not actually travel from the guitar to your ear. Instead, each individual molecule moves a small distance as it vibrates, causing the adjacent molecule to vibrate in a rippling effect. Because one particle is displaced from its equilibrium position, it exerts a push or pull on its nearest neighbors, causing them to be displaced from their equilibrium positions. Once these vibrations travel to your ear, they cause the eardrum to vibrate, which the brain translates as sound.
Let's look more closely at the waves in which the sound propagates. Sound waves propagate as longitudinal compressions in matter. Because of the longitudinal motion of the particles, there are regions where the particles are compressed together with high pressures and regions where the particles are spread apart with low pressures, known as rarefactions. To make this more clear, we've drawn a sine curve to represent the compressions and rarefactions. Obviously, sound is still a longitudinal wave.
We will now discuss the frequency of sound waves. It is important to note, as a sound wave moves through a medium, each particle vibrates with the same frequency as the original source of the sound wave. For sound waves, frequency denotes the number of vibrations of particles per time, as well as the number of compressions or rarefactions that pass a given point per unit of time. High frequencies produce high pitches, and thus low frequencies produce low pitches.
Next, we will talk about loudness and intensity. The more energy a sound has, the louder a sound seems. The intensity of the sound is the amount of energy that is transported past a given area in the medium per unit of time. As a result, the greater the amplitude of vibrations of the particles of the medium, the greater the energy, and the louder, more amplified the sound is. So as you can see, louder sounds have larger amplitudes. The scale for measuring intensity is known as the decibel system.
Finally, we will mention the quality of sound. Pleasant sounds have a regular wave pattern which is repeated. This is why test tones are always nice, smooth waves which are ideal for technical purposes. In contrast, noise have waves that are irregular and do not repeat.